Right, thank you. So I'm Nacy. I'm an air quality modeler with the Utah Division of Air Quality. And today I'm going to talk about air quality modeling simulations we did for summertime surface ozone along the Wasatch Front. So this modeling was done in support of the state implementation plan, the ozone SIP for the Wasatch Front. Both Becky and Ryan talked about that in the morning when in non-attainment ozone. And so the modeling we did is to help inform policy, help them determine what kind of controls we can do for to bring down ozone into attainment. So what I'm going to talk about is I'm going to discuss results from our model performance evaluation, which basically tells us how well the model is able to simulate observations. And I'm also going to talk about how sensitive the model is to a change to air perturbation emission inputs. And more importantly, what does that mean for control regulations? What are the implications of model performance on how we are modeling the effectiveness of controls? So for our modeling, we considered 3 domains: a 12-kilometer domain that covers the western US, a 4-kilometer domain that covers the entire state of Utah and parts of neighboring states, and a higher resolution 1.33-kilometer domain that is focused on the non-attainment area, which is the ozone non-attainment area, which is the region of interest in this exercise. So for model configuration, so how did we configure the model? We used ChemX V7.1 for our photochemical modeling. The episode we're simulating is a summertime episode that occurred in 2017. For the 12, we ran the 12-kilometer domain alone, as standalone, where we used the boundary conditions from geochem modeling that Rambo did for us. For the 4 and 1.63-kilometer domains, we ran these in a two-way interaction mode. And boundary conditions for these were derived from the 12-kilometer domain. For gas phase chemistry, we use the CB6R5 chemical mechanism. This is the, I think it's the latest chemical mechanism in ChemX, but it does not include halogens chemistry. Meteorological outputs or inputs were derived from WRF, where we used a hybrid vertical coordinate system to better represent the complexity of the terrain. In Utah, we had 44 vertical layers, and we adjusted vertical diffusivity over urban areas to enhance mixing that happens overnight. And for emissions, MOVE3 was used for on-road, non-road mobile emissions modeling. We use VCPI for estimating emissions from VCPs, and BIOGENIC using BIOS 3.6 and BELD-BOUNTIFUL. So for model performance, so we did that by comparing model outputs to measurements, and we focused on specifically 3 of our DAQ stations. Bountiful, that's a station that is influenced by emissions from industrial sources in the area, like the refineries, and also by typical urban sources. Hawthorne is more of a influenced by urban emissions, and then Urda is very different. It's more like a rural site with less influence from anthropogenic sources. And of course, all 3 could be impacted by the lake breeze. So the idea behind the different sites is that they will help us understand different components of the model. So for model performance, we started looking at the model maximum daily 8-hour average ozone. So here you're looking at modeled in red versus observed in gray at Bountiful, Hawthorne, and Urda. And as you can see, the model tends to overall replicate well the temporal variation in ozone, but it underestimates this maximum daily 8-hour average ozone. And that underestimation is obvious at all 3 sites. So the question now is, what is causing this underestimation? Are we underestimating background ozone, or are we underestimating local production? So we further looked into that. Following Rambo's approach, we looked at the temporal variation in maximum daily 8-hour average ozone at a site in Colorado, which is a high altitude site that is constantly measuring metropospheric air. So it's basically measurements at this site are a good representation of background emissions. And you can see that for the period that the model usually, it does, for the most part, it does seem there's some overestimation in modeled ozone for background, not very significant, but some overestimation. And for that, those same period where we're overestimating the background, local ozone at our monitoring stations actually underestimated. So kind of suggesting that this underestimation that we're seeing at our local stations is driven by an underestimation local ozone production. So then the question became, what are we underestimating? What local emissions are we, or local ozone precursors we're underestimating? So we looked at biogenics. So what we did here, we did a sensitivity simulation where we ran CAMX twice, once with the BIOGENIC 36 BELD-41 model for estimating biogenics, and another time using BIOGENIC 37 BELD-5. So BIOS BELD is basically the model that is typically used for biogenic emissions and for estimating biogenics. And one big difference between the two versions is that in the most recent version, the emission factor and leaf area index for isoprene for urban land use increased significantly by a factor of almost 300 times. And what we're saying, these results here, we're comparing model outputs from those two simulations in red and blue versus observed for formaldehyde, isoprene, and then looking at their impact on ozone. And this is at just the Bountiful site where we have measurements. And what we're seeing is that with the oldest version of BIOS and BELD, we actually see better agreement between measurements and model outputs. And for isoprene, you can clearly see how we're really overestimating isoprene with the latest version. Now, of course, those are only a few data points. That's the only data we have available from for that 2017 time period that we're simulating. But still, if we go down looking at ozone throughout the episode, it does seem that with the older BIOS BELD, we see better ozone performance at Bountiful. So, which is why we picked this BIOS 36 BELD-41 for our model performance evaluation. But clearly, we're still not well representing old species like formaldehyde, which could have sources other than biogenics. So next, we looked at the temporal trend in isoprene. So here we're looking at the hourly trend in isoprene at Hawthorne modeled versus measurements from summer 2021. The top two also at Hawthorne, and the lower one is measurements at the U of U site during winter 2017. And while these field measurements cannot be really compared to our day-specific 2017 measurements because of the difference in years, they're qualitatively useful to see if we're modeling this trend in isoprene well. And I should say, I guess, we have to say that we didn't have any continuous 2017 measurements, which is why we're looking at 2021. And you could see here that in the measurements, we kind of see a peak in isoprene that is happening around 8 p.m. And even it seems a bit also obvious in winter, but not as pronounced. And we're not capturing that peak in our modeling simulations. It's possible that maybe this is related to transport, and perhaps we're not modeling well transport in the model. So maybe transport from, I don't know, could be the lake, could be mountain flows, unclear, but obviously we're not representing isoprene temporally well in the model. And also it seems to sustain stay high around midday, which we don't really see in the 2021 measurements. So maybe suggesting that isoprene is not oxidizing to other species, maybe due to lack of oxidants. Still need to investigate that, but I guess the conclusion here, not very well representing isoprene. So we then shift focus to look at halogens, the impact of halogens on ozone formation in the valley. NOAA did an analysis on the 2017 aircraft measurements that clearly showed that halogens emissions from US magnesium, which is an industrial source on the west side of the Great Salt Lake, with significant emissions of halogens. They showed that halogen emissions from this US magnesium, locally, they just close to the plant, they cause depletion of ozone, but as the plume from US magnesium makes its way around the lake and makes its way around the lake, that ozone starts recovering. And then as the plume reaches the urban valley, where it mixes NOx and VOCs, they start seeing an increase in halogens, which, an increase in radicals, and subsequently an increase in ozone. And for that case, wintertime PM2.5. So now we're wondering if that same chemistry is happening in the summer. So what we did, again, we did a sensitivity analysis, but this time we ran ChemX twice, one with and one without halogens from US magnesium. For this run, we reverted back to CP6R2H chemical mechanism in ChemX. So it's older than CP6R5, but it does include the full halogens chemistry, which now Ramble is in the process of developing CP6R5H for us. So we'll at some point rerun this. But what we're seeing is that when we include halogens, this is here looking at the difference in ozone between the two runs with and without halogens. And when we include halogens, ozone close to US magnesium, which is here, is clearly depleted. But then as the plume makes its way, we start seeing formation ozone. So positive change here means formation ozone. And as the plume makes its way down, starts interacting NOx and VOCs, we see even more ozone formation. And the same area we see the increase in ozone corresponds to the area with high NOx as well as high formaldehyde, which makes sense considering the chemistry. And I guess in conclusion, so the model is doing an okay job replicating the temporal variation in ozone, but we are underestimating local ozone production, possibly related to underestimation in oxygenated VOCs or maybe just formaldehyde in this case. And we are not well representing isoprene. Moving forward, we're going to keep looking at the halogens emissions. We're going to do plume dispersion modeling to see how well the model is actually replicating the plume transport. Then some point implement CP6R5H. And from that, we're going to move on to looking at the Great Salt Lake, how that impacts ozone formation. Thank you.
Do you have any questions? Oh. Do you want me to throw it or can I walk and hand it to you? Did you have a question? Oh no, I thought I saw your hand up. Okay. Oh, over here. Okay. I'm running. Okay. I'm so sorry if I hate.
I'm good. Okay, so on your isoprene, in your model, do you have any sense of how much isoprene was turning over in your model? Like, what was your emission profile look like? Because it looks like the emission profile for isoprene without oxidation.
Yeah, I mean, yeah, so I guess your question is how much of the chemistry is happening?
Well, I mean, so like, do you have a sense in your model what your emission profile looks like compared to what, you know, if, for instance, if oxidation was off for isoprene? Because you're seeing an early morning peak as things heat up in the sun, you know, we get a response to sunlight and a response to temperature for isoprene production. And so those are two different things because it basically looks like your emission profile, your actual measurements look good in terms of they start to come up, oxidation kicks in, isoprene goes away because it's being oxidized. It's a molecular reaction rate with OH. And then you get a peak after the sun starts to go down and oxidation slows down.
Right.
So
yeah. So for us, you're right. I mean, this profile is more like consistent with more emissions, at least in the morning. And then for midday, it kind of, whatever isoprene is formed is sustained. So I don't think it's actually being oxidized. Possibly, maybe we don't have enough oxidants in the model because in the measurements, you don't have really that midday peak.